Okay, let's get started with today's lecture. Welcome to this live interactive session on the course Fluid and Particle Mechanics offered on NPTEL powered by SWAYAM. This course is offered by Professor Sumesh Thampi and Professor Basavaraj from the Department of Chemical Engineering in IIT Madras. I am Shankaraj. I'll be your teaching assistant for these sessions, which happens on Mondays from 6 o'clock to 8 o'clock. So, with that said, let us get started with the questions for this week. Okay, now in week 5, as we were discussed in a couple of weeks earlier, was related to similarity and non-dimensional analysis. And let's start with the assignment questions that were due on a couple of weeks before, or last week. I think 16th was the deadline, or 23rd was the deadline for these assignments. And yeah, let's get started with the week 5 assignments. So yeah, these are the graded assignments. First question is, consider the figure that is given below, this figure, and which of the following statements are true is the question. First is, shapes given in the figure are geometrically similar. Second one, shapes given in the figure are geometrically dissimilar. Third one, comment about geometrical similarity can be made if and only if the ratio of V2 by V1, V3 by V1, etc. are known. The fourth one is, comment about geometrical similarity can only be made if Reynolds number is known. Which of the following answers are correct? I'll give you a minute to think about it. Let's see if we can answer it. So, let's look at each option that is given below. Shapes given in the figure are geometrically similar. We see that these sides are this area represents a star, and each of these smaller uh, versions represents a scaled or a lowered version or a scaled version of a star, or a mini version of this bigger star. Therefore, we can say that these shapes that are given are in fact geometrically similar because they all are looking like a star. The shapes given in the figure are geometrically dissimilar, therefore renders it incorrect. Third option, comment about geometrical similarity can only be made if the ratio of V2 by V1, V3 by V1, etc. are known. That statement is incorrect because we don't need to know what the ratio of V3 to V1 or V2 to V1 is. We can just say that the sides are all the same. The area will be again obviously different, but the angle made by these sides are all will be the same. And yeah, therefore we can say that geometrical, this option C is incorrect. And geometrical similarity can only be made if the Reynolds number is not known. Reynolds number has nothing to do with geometrical similarity. In fact, it has very little to do with kinetic similarity as well. We'll come to that in the next couple of questions. But yeah, the correct answer is the option A. Let's go to question number 2. Which of the following statement is wrong? Option A, kinetic similarity automatically implies geometric similarity. Option B, the motion of two systems are similar if homologous particles lie at homologous points at homologous times. Option C, the dynamic similarity ensures that all the forces are in the same ratio and have equivalent directions between the model and the prototype. Option D, the dynamic similarity automatically implies kinematic similarity. Option E, kinematic similarity requires that the model and the prototype have same length scale and same time scale ratio. Option F, in two geometrically similar shapes, the absolute value of the angle will also be the same. Option H, option G, flow conditions for a model are completely similar if all relevant dimensional parameters have the corresponding values for the model and the prototype. Option H, all the technical statements in this section are wrong. Option I, option H is all the statements in this section are correct. Option I is all the technical statements in this section are wrong. So, what is the correct answer here? I'll give you a minute to think about it. Okay, so the correct answer here would be all technical statements in this section are wrong. Let us see why the answer comes out to be that way. Now, kinematic similarity automatically implies geometric similarity. That statement may not be correct because kinematically similar does not mean that it is geometrically similar as well. The motions of two systems are similar if homologous particles lie at homologous points at homologous times. That also we cannot say. Therefore, if we consider each and every option, you'll see that all the options are in fact wrong. Therefore, the correct option is all technical statements in this section are wrong. But I'll have to check back with you why most of these statements are wrong, because I feel that most of these statements are in fact correct, and I think I'm unable to explain properly why all of on this. But until then, I'm just telling you what the answer is given as per the Swayam website. Okay, let's move on to question 3. A 1/6 scale model of an automobile is to be tested in a wind tunnel at a speed corresponding to the prototype speed of 60 km per hour. Assuming that only inertial and viscous forces are to be modeled, calculate the following. According to the question, which among the following numbers need to be same in order to perform this comparison? Reynolds number, Froude number, Weber number, or Mach number. Which of the following numbers need to be same in order to perform the following comparison? I'll give you a minute to think about it. The key point is that only inertial and viscous forces are to be modeled. Okay, let's find the answer here now. The correct answer is in fact Reynolds number. As Reynolds number is given as a ratio of inertial forces to the ratio of viscous forces. Froude number is in fact the ratio of inertial forces to the force of gravity. Weber number is in fact the Weber number is used when there is an interface between two different fluids, and it is measured as it is a ratio of this is actually the square root of ratio of inertial force to the surface tension force. And Mach number is basically the speed of the fluid to the speed of sound in that medium. And generally, Froude number refers to how dominant gravity is with respect to inertial force. Weber number refers to how dominant surface tension and inertial forces are. And Mach number generally gives idea about something that you've already heard. It is known as incompressibility. So whether a flow is incompressible or not comes from the idea of Mach number. Therefore, in the following in the question that is given, there we have to match the inertial and the viscous forces. Reynolds number is the correct answer. Okay, we'll move on to the next question. Again, it's based on the same starting write-up that has been given to the previous question, where 1/6 model of an automobile is used in an wind tunnel. Now the question is, what should be the wind speed at which the model automobile should be tested? Note that the fluid around the model and the model automobile and the prototype is the same and is air. Report your answer in kilometer per hour. So what is given here is that the prototype model is 60 kilometer per hour. Prototype air is equal to the same as model air. Prototype viscosity is the same, but the there is a scaling for the length scale, which is a 1/6 model. The prototype has to be taken in a place, is being taken up in a place where the diameter of the prototype is 1/6 the times of the diameter of the model. Therefore, when we equate, what should we equate here? Therefore, we know that since we are equating the dimensionless numbers, as we said here, we have to compare the Reynolds number in both the cases. Therefore, Reynolds number is given by rho m, and for the particle it is given by rho p vp dp by mu p, and we are equating that with the Reynolds number of the model, which is given by rho m um dm by mu m. And as shown here, as shown here, we can equate and cancel off the density in the left and right. Therefore, we can just say that UP times dP should be equal to UM times dm. And we know that dP is 1/6 times the dm, and we know that UP is 60 kilometer per hour. So 60 times oh, sorry, I think I made a mistake here. We should have written the prototype is 1/6 that size of the model. Yeah, so we'll get 60 into 60 times 1 is equal to 1/6 times the model velocity. Therefore, the model velocity will come out to be yeah, I think I made a mistake here. We know that the model has to match the sixth scale. So yeah, it is given here that 1/6 scale model of a prototype. So the diameter of the model is in fact 1/6 times the diameter of the prototype. Therefore, the model automobile will have a velocity of 360 km/h. Okay, question number 5. If the model drag at that speed is 510 Newton, what will be the drag on the prototype? Report your answer in Newton. So how do we do this now? Please give you a minute to think about it before I give you the answer. Okay, for this, what we do is we in fact equate the drag coefficient on the model to the drag coefficient on the prototype. Since it is given that what we have to find out the model drag on the prototype, we equate the drag coefficients of the model and the prototype. And the equation for drag coefficient is given by the drag force to the ratio of rho v square d square. And similarly, we write this the equation for the drag coefficient on the prototype as well. Now it is given that the model drag is 510 Newton, and it is known that the densities are the same, and we also have equated u times d of the model to be equal to u times d of the prototype. So these all cancel out, and we end up with the final answer for the drag force on the prototype to be equal to 510 Newton. Therefore, the correct answer is 510 Newton. Okay, let's move on to question number 6. What is the power requirement required to overcome the wind drag of the prototype automobile? Report your answer in kilo. How will we do this question? I'll give you a minute to think about it before I give you the answer myself. So for this, we need to understand that the power requirement P is basically the drag force times the velocity, and for this is as for the prototype, so we just write this as FDP times Vp. And we know that the drag force is 510 Newton, which is written down here, times the velocity of the prototype we have found out to be equal to 360 kilometer per hour. Now we need to convert this kilometer per hour into meter per second or in the SI units. So we multiply it with a number that is. So what we do is 1 hour in 1 hour has 3,600 seconds, and 1 kilometer has 1,000 meters. Therefore, we'll get this through a simple multiplication. We'll get the power requirement. Sorry, this is not FD, this is power required. Oh, sorry, I shouldn't have written down this here. In fact, it goes here, 510 into 360 kilometer per hour times 1000 by 3600 meters per kilometer and seconds per hour. Therefore, we'll get this as 8500 in the SI unit, which is watts, which is 8.5 kilowatts, which is the answer for this question. Okay, let's move on to the next question. A simple approach to consider the effect of particle shape in fluid particle system is through sphericity. Consider a cube with each side of 1 micron length. Density of the cube shaped particle is 1000 kilogram per meter cube. Calculate the sphericity of particle. Now the sphericity phi is defined as surface area of a sphere with the same volume as that of the particle divided by the surface area of the particle. Although this equation looks so big, it's not very tough, but it is very quite straightforward. Now, for a cube and cylinder, we'll find it out first. Then I'll explain to you why sphericity is important. So first, we have to equate and find a sphere with a ray with a diameter such that the volume of the sphere matches the volume of the particle. And here, the particle volume given by Vp is equal to 6 times a cube, which is 6 into 10 raised to minus 6 whole cube, which is 6 into 10 raised to minus 18. And since this is in meters, this will be in meter cube. Now what we need to do is we need to find of a sphere which has the exact volume of this particle, which is 6 into 10 raised to minus 18. Therefore, we find the volume of sphere to be equal to 6 into 10 raised to minus 18, which is equal to pi times, let's call the diameter of the sphere as ds, cube by 6. Therefore, before we finish doing the mathematics, we'll just write ds as cube root of 6 by pi times 6 into 10 raised to minus 18 meters. Let this be the diameter of the pipe of the sphere with the same volume as that of the particle. In fact, you will get this value as 1.24 into 10 raised to minus 6 meter. Now, what is interesting to note here is that the area for surface area for a sphere is given by pi d square or ds square, which is pi times 1.24 into 10 raised to minus 6 meters the whole square. And the surface area of a cube is, or of a particle is equal to, oh, I'm so sorry, this is not 6a cube, this is just a cube. And surface area of the particle will be equal to 6a square, which is 6 into 10 raised to minus 6 meters the whole square, which is 6 into 10 raised to minus 2. Therefore, the sphericity of the particle is now given by the surface area of the sphere divided by the surface area of the particle, which turns out to be pi into 1.24 into 10 raised to minus 6 the whole square divided by 6 into 10 raised to minus 2. And this value will turn out to be 0.806. So why do we do this sphericity calculations? I think it is quite obvious in the class from what is discussed in the class. Basically, if you have a volume, then the surface, if you have a particle with a specific volume, then the smallest surface area will be that for a sphere. It will be very much less than any other particle with any other shape that you take. So that is basically the reason why a surface area of the sphere to the surface area of particle with the same volume as that of the sphere. Basically, if we equate the volume of the particle to the sphere, and this sphere will have the surface area or have the minimum surface area for any kind of particle. If it's a perfectly spherical particle, then the sphericity of the particle will be equal to 1. Any other shape will have a sphericity that is less than 1. Therefore, if you have some weird looking shape such as a rock, yeah, such as a rock, and that doesn't look too spherical, we'll have a sphericity less than 1. It even works for shapes such as a dumbbell like shape where it's uh, not at all uh, spherical. Yeah, so this is how the sphericity works, but yeah, I'm sure this was pretty much covered in class as well. So let's move on to question number 8, where it's a series of very simple questions. Pick out the correct SI unit, standard international unit of surface area from the volume from the following. It is very fairly easy. It is meter square and it is not meter cube, which is the SI unit for volume. 1 by meter square is the inverse of volume, and 1 by meter cube is the 1 by meter square is the inverse of surface area. 1 by meter cube is the inverse of volume. Now, next question is pick out the correct surface area. So this specific surface area, or whatever it is, specific volume or whatever it is, refers to per kilogram or per gram or whatever, per volume, per mass basis. Whenever something is specific conductivity refers to conductivity per mass, similarly specific surface area refers to surface area per kilogram. And we know that the surface area unit is meter square, therefore the correct SI unit for the specific surface area is meter square per gram. Next question is, calculate the specific surface area in SI units of a spherical silica particle of 1 micron diameter and density equal to 2000 kilogram per meter cube. How do we do this question now? I'll give you a minute to think about it and then I'll give you the answer. Okay, so in order to answer this question, we need to first find out uh, the surface area of the spherical particle, and let's write down. So the specific surface area, or I'll just write it as SPSA from next time onwards. It is given by the surface area of the particle to the density of the particle, and density is given by kilogram per meter cube times the volume of the particle. So the density times the volume will in fact be the mass of the particle. And it is given that it is a spherical silica particle. So for spherical particle, we can simplify this surface area as pi d square divided by rho p times pi d cube by 6. Therefore, this equation would simplify down to 6 by rho d or rho p dp, and the values can be put here where the density is 2000 kilogram per meter cube times the diameter of the particle, which is 10 raised to minus 6 meter. Therefore, you'll get this answer as 3000 meter square per kilogram. Okay, let's move on to the next question. When tested in water at 20 degrees Celsius flowing at 2 meter per second, an 8 centimeter diameter sphere has a measured drag of 5 Newton. Use this information to make predictions for a 1.5 meter diameter weather balloon moved in sea level standard air under dynamically similar conditions. First question is, what will be the velocity of the balloon if the balloon is similar to the sphere? Now again, we need to note that this is part of the practice problems, so this is not part of the graded assignments, and this will not go towards the final grading that is there. So first, what we need to understand is we need to understand which dimensionless number that we have to use, and that is in fact the Reynolds number. So we can say that the Reynolds number of the sphere should be equal to Reynolds number of the balloon. Therefore, we can say that the it is dynamically similar to the sphere. Therefore, we are using the similarity of Reynolds number. But we have to understand that this is first the 8 centimeter diameter sphere is tested in water at 20 degrees Celsius, and therefore we'll just make that note. Water is roughly 1000 kilogram per meter cube. Viscosity is 1 centipoise, which is 0.001 in the SI units, which is kilogram per meter second. And the velocity of the sphere is 2 meter per second, and the diameter of the sphere is 0.08 meters. On the other hand, let's consider the weather balloon, which is in a sea level standard air and for that the density of air at sea level can be taken as 1.225 kilograms per meter cube. The viscosity of air can be found out to be 1.78 into 10 raised to minus 5 kilogram per meter second, and the diameter of the balloon is 1.5 meters. What we need to find out is the velocity of the balloon. Now we have all the data here. We just need to equate and find out. What is not actually given directly in the question is that is the density and viscosity of water and density and viscosity of sea level standard air. That we need to find out either from Google or any other handbook or Paris handbook can be used here. But we can just Google it out in this day and age. Therefore, when we equate the Reynolds number of the sphere to the Reynolds number of the balloon, we get this out to be equal to, when we equate it, we'll write it as 1.225 times of kilogram per meter cube times the velocity of the balloon times the diameter in meter to the viscosity as 1.78 into 10 raised to minus 5 kilogram per meter second. And we equate that to the Reynolds number of the sphere in water as 1000 kilogram per meter cube times 2 meter per second times 0.08, that is 8 centimeter, by the viscosity, which is 0.001 kilogram per meter. Therefore, you will get the velocity of the weather balloon to be roughly equal, to 1.509 meters per second. So yeah, this is the velocity of the weather balloon when it is dynamically similar to that of the sphere. Okay, let's move on to the next question. What will be the drag force on the balloon? Report your answer in SI units. Now we know that the drag force, in order to find the drag force, we need to equate the drag coefficient between the balloon and the sphere. Therefore, the drag force so the drag force on the balloon is not no need to be found out, which can be given as FdB divided by, and we know that the equation for drag force, you have the density of the balloon times the velocity of the balloon square times the diameter of the balloon square should be equal to the drag force on the sphere. Okay, this is not the density of this is density of air that comes here. Similarly, here density of water comes times velocity of the sphere in the water times the diameter of the sphere. Therefore, when we equate this, we'll get the drag force on the balloon to be equal to 5 by 1000 times yeah 2 square times 0.08 square times the density 2255 times velocity of the sphere comes out to be around, we found it as 1.509 square, let's write it as 1.509 square times the diameter of the valve balloon, which is 1.5 square. Therefore, just by simply multiplying this, we'll get the value to be approximately equal to 1.312 Newton. Okay. Next practice problem. Yeah, we are again dealing with the sphericity, but we are doing it for a cylinder. Therefore, we have again found out the equation for sphericity as phi is equal to surface area of the sphere to be divided by surface area of the cylinder. Therefore, we first find out the diameter of the sphere given by pi uh, ds cube should be pi ds cube by 6 should be equal to the volume of the sphere, which is pi dc square h 4. Therefore, we'll get ds as the cube root of the cylinder has a diameter of 1 micron and a height of 3 micron. So, therefore, 1 into 10 raised to minus 6 square times 3 into 10 raised to minus 6 divided by 4 times 6. And the diameter of the sphere I have found it out to be around 1.651 into 10 raised to minus 6 meter. Therefore, you'll get the surface area of sphere, or let's just directly calculate the sphericity, which is pi d square divided by d square by 4 plus pi dc, or 2 pi into dc square by 4 plus pi dc times h, which is the This is refers to the curved surface area, and this is the top and bottom surface area. And we can cancel out pi from everywhere, and we will get after substituting for 7. Okay, I think next will be the last problem for the practice 5. Practice problems of week 5, where we have to find the you consider a cube with each side of length 1 micron. The density of this cube is 1000 kilogram per meter cube, and you just have to calculate the specific surface area. Yeah. So for this, we know that the specific surface area is surface area per density times volume. For a cube, it is 6a square is the surface area divided by a cube is the volume times the density, which is 6 by rho times a, which in fact comes out to be same as that for the sphere of diameter d. Now substituting the value, you will get 6 by 1000 times 10 raised to minus 6, which comes out to be 6000 in the SI units, which is meter square per kilogram. Okay, I have a few more questions on this week 5, uh, which was on the non-dimensional analysis, particle characterization, Brownian motion. So let's take a look at this question, where the aerodynamic drag of a new sports car is to be predicted at a speed of 50, air temperature of 25 degrees Celsius. I think this is very important in this question. Automotive engineers built a 1/5 scale model of the car to test in a wind tunnel. It is winter and the wind tunnel is located in an unheated building, and the temperature of wind tunnel air is about 5 degrees. So there is a temperature and viscosity dependence on this. There is a dependence of viscosity and density on temperature. Next, determine how fast the engineer should run the wind tunnel in order to achieve the dynamic similarity between the model and the prototype. So, in order to achieve the dynamic similarity, as you have seen before, we just to be equal to the Reynolds number of the prototype. But what is not given is the density and viscosity, which needs to be googled out or found out from the Paris handbook. So we from that I obtained the temperature at temperature 25 degrees Celsius. I obtained the density to be equal to 1.184 kilogram per meter cube, and the viscosity to be equal to 1.849 into 10 raised to minus 5 kilogram per meter second. And this is for test in a wind tunnel. Therefore, this is for the sports car. This is at 25 degrees Celsius, and the velocity of the sports car is given as 50 miles per hour. And it is also, we can also find out it at what happens at 5 degrees to the density and viscosity. We see that the density of the air at 5 degrees is 1.269 kilogram per meter cube, which has increased, and the viscosity at 5 should be equal to 1.754 into 10 raised to minus 5 kilogram per meter second, which has decreased. This is true for for a fluid or for air, like a gaseous fluid. We just need to find out what the velocity of the model should be. Now, what else is given is that it is a 1/5 scaling model. Therefore, uh, the wind tunnel is, or the wind tunnel should be equal to 1/5 or the of the diameter of the car, or what wind tunnel should be equal to the model of the prototype, and the prototype is the sports car here. Therefore, having all the variables, you can just directly equate them. We'll get it as 1.184 in 1184 times 50 miles per hour in kilogram per meter cube times the diameter is dm divided by, or I'll just write this directly as dp by 5 by 49 into 10 raised to minus 5 kilogram per meter second should be equal to 1269 kilogram per meter cube times the model velocity times the diameter, which is dp, divided by the viscosity, which is 1.754 into 10 raised to minus 5 kilogram per meter second. From here we'll get the velocity of the model. From just by calculating, we'll get it as 221 miles per hour. Okay, we'll move on to a couple of more questions. Calculate the sphericity of cylinder. We have just done this question, so we'll move on to the next question. A prototype automobile is designed for cold and its drag force is just to be in a 1/7 scale model in a wind tunnel at 20 degrees and 1 atmosphere. If the model and prototype satisfy dynamic similarity, what prototype velocity in miles per hour is matched? So here what I am trying to find out is very similar. The only difference here, the finding out the density of the prototype and the model, which is obtained from the ideal gas law, which is given as P by RT. Therefore, the prototype is designed for a cold weather in Denver, which is minus 10 degrees Celsius at 83 kilopascal, which is 83,000 pascal, times temperature is 263 Kelvin. What is the value of R? It is 287 in joules per kilogram Kelvin. This R is equal to 287 kilogram Kelvin is for air, and similarly rho m is given by P by RT, which is at 1 atmosphere and 20 degrees Celsius, which is 101325 Pascal divided by 287 times 293. Therefore, we have the densities. We also have the viscosity of air at minus 10 degrees Celsius to be equal to 1.7 into 10 raised to 5, and viscosity of air at 20 degrees Celsius to be equal to 1.8 into 10 raised to minus 5. From here, we just need to equate the Reynolds number of the model to the Reynolds number of the prototype. Rest everything is very easy. We'll get the velocity as 22.8 miles per hour. Please, I'll give you a few minutes to focus on that. Okay, we'll finish off with a couple of more lots. Number used to correlate bubble dynamic studies is a dimensionless combination of, let's write it down while we do it. It's a dimensionless combination of gravity, viscosity, density, and surface tension Y, surface tension coefficient Y. If Morton's number is proportional to gravity, find its form. Therefore, we can write this as gravity times power 1 power times A and rho power B and Y power C. Sorry, this is not B, this is actually C. If I write it like that, then I know that Morton's number is basically dimensionless. Therefore, the product of this should be in fact remain dimensionless. Let's do that now. We'll write it as LT raised to minus 2, which is for gravity. For viscosity, it is m L raised to minus 1 T raised to minus 1 the whole power A. Density is m L raised to minus 3 power B. And what is the unit of surface tension coefficient? You know that surface tension is force per unit length. Therefore, force is mLt raised to minus 2, and that multiplied by 1 by L will give you mt raised to minus 2 power C. Therefore, we'll just have to rearrange and we'll get this as Lt raised to minus 2 mt power minus A, m power b, L power minus 3b, and m power c, t power minus 2c. Clubbing all the common terms, we'll get it as L raised to 1 minus 3b minus, sorry, L minus a minus 3b, m power a plus b, L power, sorry, only t is remaining, so t power minus a minus 2c. Therefore, we need to solve a set of equations now. We have three equations, that is a plus 3b should be equal to 1, a plus b should be equal to 0, and minus or a plus 2c should be equal to. Therefore, we will get a as 4, b as minus 1, and c as 3. Sorry, c as minus 3. Oh, there is a plus c as well here. Yes, made a small mistake over there, so I've corrected that now. Moving on to next question. The Richardson number, which correlates the production of turbulence by buoyancy, is a dimensionless combination of acceleration due to gravity. Richardson number is product of G, the fluid temperature T naught, the local temperature gradient dou T by dou Z, and the local velocity gradient dou U by dou Z. Determine the form of the Richardson number if it is proportional to G. So it is proportional to G power 1, T naught power A, dou T by dou Z power B, and dou U by dou Z power C. Therefore, again, we write this in the dimensionless form as Lt raised to minus 2. Temperature, I am denoting it by theta, theta power A, or I'll just write it as, for my sake, it is K power A. Dou T by dou Z has the unit of temperature to length, which is K L raised to minus 1 power B. Similarly, dou U by dou Z has a unit of velocity per length, which is L T raised to minus 1, L raised to minus 1, which is basically L raised to minus 1 power, T raised to minus 1 power C. So we'll get this as L T raised to minus 2, K raised to A,
Therefore, rearranging, we'll get this as L raised to 1 minus B, K raised to A plus B, and T raised to minus 2 minus C. Therefore, we'll get it as, we have to solve the following equation. 1 minus B is equal to 0, A plus B is equal to 0, minus 2 minus C should be equal to 0. And from here we'll get B is equal to 1, A is equal to minus 1, C is equal to minus 2. Therefore, the correct formula for Richardson number is given by G times B is G times dou T by dou Z divided by T naught times this is dou U by dou Z d whole square. So I'm gonna skip a couple of questions, and I think I'll end the session here. Unless you have any questions, please feel free to reach out to me. I'll be happy to answer. Anyway, this session's live interactive session will happen on every Monday from 6 o'clock to 8 o'clock. Please join the class and ask your doubts. Otherwise, you can also ask it in the Swayam portal directly. Thank you.